you can imagine that, or say it's a propane, sorry, doesn't matter. You have its electron cloud here around it, and you imagine it, say, coming in contact with some other group, some other propane group. The idea is, of course, that these electronic clouds actually want to bump up against one another. They don't want to quite overlap, but they certainly want to avoid this situation. This kind of spacing is not going to happen. You're not going to see gaps. There really aren't going to be gaps between the molecules. Instead, they're going to want to be near one another. So that's a completely different scenario. They want to be near each other. They don't want to form gaps. And so mathematically, what are we talking about? Well, to understand that, we need to think about a rather complicated concept that obviously we haven't totally learned yet, but I think it's worth thinking about. Is we need to think about energy, or potential energy. And we'll call that E of, and we're going to call potential energy as a function of distance between atoms. So R being distance. And I talked about this value before. If we had a pair of atoms, the distance between them, this van der Waals distance, we call R. So two atoms, the distance between their centers. They say center to center distance. Okay. So imagine we have this potential energy function right in the middle there. It's worth 0 kilojoules per mole of energy. And if we overlap these atoms on one extreme, so their clouds were overlapping, so the propane molecules are overlapping their electronic clouds, that is not a favorable situation. It's going to be very high in energy. Then that's going to come down, and eventually the atoms will be in a very nice configuration where they're nearly touching. Let's say they're about three-ish angstroms apart, making a good van der Waals contact. And then eventually you start to pull them apart, much like I've drawn up here. And these atoms are now very far apart, and the energy drops off to 0. There's no real interaction between these because they can't really induce a dipole within one another. They can't feel any electrostatic attraction to one another at that distance. So the energy function for this, E of R, and don't worry about, is some energy, 4 times some energy that defines the bond energy, and I'll draw that in blue here. It's an epsilon. Sorry. Don't worry about this equation. You're not going to see it on the exam. I'm just, trying to give you a heads up in the future. And, there's basically these terms. We have R, our van der Waals distance, in the denominator for a 12th power term and a 6th power term. The 12th power term is the repulsive term. So this is a repulsion. The repulsive force here, or energy, repulsive energy here is going to go with to the 12th power. And then the attractive, this is the attractive term. The attractive term here, so there's a repulsive, and this is the attractive, is something to the 1 over R to the 6th power. Okay. So, and then sigma, people that want to know what sigma is. Sigma is this distance where the energy is exactly 0. Okay. Don't worry about it too much. But the idea I think you should pull away from this qualitatively is that these van der Waals interactions are most stable when the electronic clouds are just right so near one another, not overlapping too much, not too far apart, and so they can have this, they have these dipolar interactions or induced dipolar interactions with the neighboring molecular system. Okay. And those distances are on the order of say 3 angstroms for they say carbon to carbon if you had hydrocarbons. All right. And just put one more note here. This is the perfect van der Waals interaction distance. And this is unstable. All right, so that's that, and we'll, so now let's think about our hydrophobic interactions. And what I was trying to allude to before is that hydrophobic interactions are, like I say, first and foremost, the most basic way of thinking about it. It's a surface area phenomenon. The more surface area, hydrophobic surface area you have exposed to water, the less favorable that situation is. And so if you can bury hydrophobic surface, you reach a lower energy minimized state configuration. And so that's why the hydrophobes want to duck and cover out, get away from water, because really it's about water just doesn't like to form those networks of strained hydrogen bonding interactions. So if you had a hydrophobe, if you had a hydrophobe and you had these waters around it, and they're making, obviously it's really difficult to draw perfectly a strained hydrogen bonding interaction, but we'll say we have strained water hydrogen bonding network. So we have a strained hydrogen bonding network around our hydrophobe. And you can imagine that if you took this, and you had this is one possible configuration, and you can imagine on the other hand you had this situation where a bunch of hydrophobes have come together. So let's say our hydrophobes have coalesced. And what happened when that occurred is that the waters were released. Okay, so I'm just going to draw the waters down here. Water was released to bulk solvent. That's a was. I'm sorry about that. So the water was released to bulk solvent, and so you might say, well, why is one more favorable than the other? Well, the reason is if you think about that, this network here, each water, say, can only exist. Each water can have, say, 2 configurations. Okay. On this side, in the strained network, you only get 2 possibilities per water. Okay, but on this side, in bulk water, not to say in bulk, each water can have, say, I don't know, whatever you'd like to use, say 5 configurations, just something more. So there's many more probable states that it could be in that water when it's released to bulk solvent. And so if you have many waters, and we imagine in a polymer, let's say you release say X number of say 6 or 7 waters per hydrophobe, and you have 10 of those, you have like say 70 waters, then you're talking about a number that gets quite large. say 5 over 2 to the 70th power, okay, states, or ratio of states, that you would gain all these possibilities if you buried your hydrophobes and released these waters. And gaining possibilities in chemistry means that's much more probable that reaction is going to take place, okay? And for, people might not, believe, that's true, but I mean, I like to say in the previous class, I came up with this analogy just standing here, but if you think about your dorm room closet, okay, when you first arrive, can someone tell me what their dorm room closet looks when they first get into their dorm and they first set it up? Anyone? What, empty? Well, empty is very organized, but I mean, when you first put stuff in, it's neat. Neatly organized or not? Or you just chuck it in? Not all of us treat our closets the same way. So she's good. This is a neat person here in the front row. What's your name? Josephine is neat and orderly. That is a very high energy situation, okay? To have that organized, neat closet, that is like, that's that water hydrogen bonding network around a hydrophobe, okay? And we know that as the semester progresses and exams happen, what happens to the closet? It's everywhere. The closet goes everywhere. That is what that closet is trying to reach the happy state that it wants to be in, completely disorganized. Just like water, when it's released from these hydrophobes, it's like, oh man, I want to get out of this organized, uptight, hydrophobic world, and I just want to fly off into solution. And that is why the hydrophobic effect occurs, and it's going to happen in your closet. I guarantee it. All right, so we have a few minutes left for that clicker question, which is very straightforward. Get out your clickers, and I'll energize it. Huh? I wish I could, but no, I don't have any explosions planned. You guys get to burn stuff, so you should be excited. Okay, don't press any buttons. Oh, people are pressing. They already know the answer. All right, hopefully you didn't try to talk to your friends from Wednesday because I changed it a little. No, I'm just teasing. So, all right, so I had to hand draw this question. Clicker question. Okay, consider this pair of interacting atoms with overlapping electron clouds. Which position in the energy diagram corresponds to this configuration? There's A on the left, B down there in the well, and C way out there in the distance. So make your decision. Choose wisely. Okay, looks like we reached. Oh, there's a few more. Click in. I'll give you till 2 minutes. Still clicking in. All right. So here's the answer, because I'm sure that everyone knew. One person voted D. Come see me after class. So yes, and the nice thing about putting up an easy question is I don't even have to grade it because you guys obviously were paying attention. That the overlapping electron clouds are unfavorable. You're putting a bunch of negatively charged electrons near each other. That's not good. So that's there on the left, the high energy state. The stable state in the well is where the two electron clouds are just near one another to polarize each other, let's say, and have an attractive dipole-dipole interaction. When you pull them very far apart, there's absolutely no interaction energy at all, and our energy diagram, our energy goes to 0. So all right, that's the end of the lecture, and have fun in lab.